So we are in a new chapter about time preferences. So the questions that I cover today are based on the third homework. So I try to make, so in the homework, you have question where beta is 0.5. I just changed that to 1/3. And then more importantly, I want to go step by step how to solve a model with beta delta preferences. Okay. So let me begin. Okay. So yeah, it's mostly about time inconsistency. Inconsistency. Okay. So let's see how we have time inconsistent agents. Okay. So let me highlight the assumptions. Beta equals to 1/3, delta equals to 1, and we have log utility. So yes. So I just saw a question by a Christian. Yes. So I also have a discussion at 7. And then you start a cake on day 1. You start with a cake on day 1. So there's 1 cake, and then you have to eat over days 1, 2, 3. So we have 3 period. Okay. So we start by assuming a naive agent. So this is the first set of the question. And in the second question, we are assuming a sophisticated agent. Okay. And then that's it. And then I made a bonus question. I'm not sure if I will have time to go over this. If not, then I'll just write the answer key for this one. Yeah. But it may be a little bit difficult for you. Okay, so question 1, we are assuming a naive agent. Now let me start with question 1A. What is the difference between naive and sophisticated agents? So if you want to solve this question, then you should know what naive and sophisticated agents are. So let me explain that first. Does anyone know the difference? Sophisticated. So for naive agents, they are naive. Naive about how my future self will behave. Okay? So does not know that beta will be 1/3 in the future. Sophisticated, they fully know about their time inconsistency. So know that beta equals to 1/3 for the future agents. If this is not clear, let me give you a diagram as an example. So day 1, day 2, and day 3. Okay, so you're thinking about, so you make a choice on day 1 with a cake. This is a cake. And then you want to split cake over 3 days. Okay, and then at day 1, you put a high weight for the consumption today. Okay, so you put high weight on consumption at day 1. Okay, so if I'm thinking of benefits between eating today and saving for later, I put higher weight at day 1. Okay, and then I discount the future value of the cakes by 1/3. So suppose that my level of happiness was 100. This has been discounted by 1/3. Okay. And then now it matters that how my future self will behave. Okay? So suppose that on day 2, suppose that the day 2 guy is very greedy guy. Okay, and then he will discount the benefit of day 3 by 1/3. Okay. Then on day 1, because I know that the June on day 2 has also beta of 1/3, I might prepare a large amount of savings of cakes. Okay. But if I'm a naive guy, I'm thinking that even if I give small amount to the June living in day 2, he will split equally the cakes between day 2 and day 3. So I don't need to give him large amount of cakes today. So I'm gonna eat a very large portion of cake today, and then day 2 June, we'll be splitting the cake almost equally between day 2 and day 3. So that is the naive agent. Okay. And then if you're sophisticated, you know that you are going to be greedy in the future. So you might want to save more today. Okay. So just in one sentence, what is the difference between naive and sophisticated agents? If you are naive, then you don't know anything about the level of beta in the future. So naive agent thinks that beta equals to 1 in the future. So not present biased. If you're sophisticated, then you know that in the future you'll discount the benefit by 1/3. Does that make sense? Okay. So do you know, or do you don't know about beta of the future? It's splitting naive versus sophisticated agents. So on day 1, what kind of problem will the naive agent solve? So this guy will be solving a problem like this: maximize log of consumption today plus beta delta log of consumption tomorrow plus beta delta squared log of consumption on day 3, where subject to, so this s dot t dot means subject to. So there's a condition here, C1 plus C2 plus C3. So consumption of cakes on day 1, consumption of cake at day 2, consumption of cake at day 3 should add up to 1. I have one cake. So here, so I'm just solving this by controlling C1, C2, and C3. I'm controlling portions of cake that I will eat on day 1, day 2, and day 3. Okay. And then on day 1, when solving this problem, naive agent thinks that the future agent will follow through the plans. Follow through the plans. So if I make a plan at once like this, he's naively thinking that June living in day 2 and day 3, we're gonna keep my plan. To keep the plan that is made on day 1, which is not true. Okay. Any questions? Okay. So this is what the naive agent will solve. And then let me set the Lagrangian and then find the first order conditions. Okay. So when you face this kind of questions in economics, the first step that we do is setting up a Lagrangian. So this wiggly L, it just stands for Lagrangian. Okay. And then we have what we want to optimize. Beta delta log of C2. Beta delta squared log of C3 plus lambda 1 minus C1 minus C2 minus C3. Now, if you don't know where this is coming from, it's just, this is like the constraint. Okay, so my cake at day 1, 2, 3 should add up to 1. So this is what it is saying. Okay. And then this is so this is not a mathematical economics class. So I will not gonna like deep dive about what this lambda means, but it's something like the value of this constraint. Yeah, so you can think that there should be some value of what I want to optimize versus value of this constraint. Lambda is kind of controlling which one is more important. Yeah. So there's some lambda here, and then this one is what I want to maximize. Any questions? Okay. So the first order conditions, let me call it FOC, first order conditions. So because we have three control, so we have three things to control here, C1, C2, and C3. So I should be differentiating with three variables. So first, differentiate with respect to C1, and I set that to 0. Differentiate with respect to C2, set that to 0. Differentiate with respect to C3, set that to 0. So if I differentiate this above equation that I circled, then if I differentiate with respect to C1, then I will have 1 over C1 minus lambda. Okay, so you can see that C1 appears here and here. So we have 1 over C1. So if I differentiate some function like lambda, log, then if I differentiate with respect to C, then I will have 1 over C. So our proof is not very difficult, but yeah, just for this class, you can just remember this. If I differentiate this log function, I will have 1 over C. Okay. And then if I differentiate this Lagrangian with respect to C2, then I will have beta delta minus lambda. Then if I differentiate with respect to C3, then I will have beta delta squared 1 over C3 minus lambda. Okay. And then so this is the end. And then we have, so now we just need to rearrange the equations and then find the solutions. Okay. Oh, I missed one thing. So when we state first order conditions, it's also good to state what the budget constraint is. So it was consumption of cake at day 1, 2, 3 as up to 1. Okay. So this is like differentiating Lagrangian with respect to lambda. Any questions? Okay. So this is like step 2. And in step 3, now we rearrange first order conditions and find the plans for consumptions C1, C2, and C3. Okay. So using FOCs, we have, so if I copy and paste this part above, like this, copy, paste, we have this one, paste, this one. Okay, so the first one, let me use color red. If I multiply both hand side, so this is just 1 over C1 equals to lambda. So this becomes C1 equals to 1 over lambda. Okay. And then also, this is C2 equals to beta delta over lambda. Beta delta over lambda. Oh, am I going too fast? Okay, so this one, so this step, I was multiplying both hand sides by C2 and then dividing by lambda again. And then for this one, C3 equals to beta delta squared divided by lambda. Okay. And then we can see that if I combine this one and this one, I have C2 equals to beta delta over lambda. Because 1 over lambda is C1, I have beta delta C1 here. And then for C3, if I combine this, then we have C3 equals to beta delta squared over lambda, which is beta delta squared C1. Okay, so we're almost done. And plugging in into budget constraint, which says that consumption of cake on day 1, 2, 3 as of 1, we have 1 equals to C1 plus beta delta C1 plus beta delta squared C1. If you're wondering where this is coming from, this one was C2, this one was C3. By what we did above, we have this equation, and then we have 1 equals to, this equals to 1 plus beta delta squared C1. Hence, C1 is 1 over 1 plus beta delta squared. Any questions? Okay. And then C2, let me migrate to here. Now C2, this is beta delta times C1 by what we did here. So it's just multiplying beta delta to what we computed above. And C3 is beta delta squared C1, which is just beta delta squared 1 plus beta delta squared. Okay. So what is this? This is the plan of consumptions of a naive agent. He is thinking that when I solve this problem, day 2 and day 3 guys will follow through my plan. And then, and after solving this, we have this solutions C1, C2, and C3. So these are the plans. What C1 is expecting to consume on day 2, day 3, and day 1. Any questions? Now let's see if this plan will be the same as actual consumption. So let's see. So on day 2, so first let me find out how much cake is left. So we had 1 cake, and then what is consumed on day 1 is C1. So 1 minus C1 is how much the cake is left for day 2 and day 3. And this is just 1 minus 1 over 1 plus beta delta plus beta delta squared, which is beta delta plus beta delta squared, 1 plus beta delta plus beta delta squared. Okay, so this is the amount of cake left. Oh, I just realized that we are assuming beta equals to 1/3 and delta equals to 1. And I'm solving a general case. I just realized this. So if you want a numerical solution, then you can just substitute beta equals to 1/3 and delta equals to 1. Okay? So for C1 plan, we will have 1 over 1 plus 1/3 plus 1/3, which is, if I do it quickly, it will be 3 over 5. This is 1 over 5. This is 1 over 5. Yeah. So if you plug in the numbers, then I think you'll have the same answers like me. And then how much cake is left? C1 was 3/5. So cake left for day 2 will be 2 over 5. So when you're facing this in the exam, because we have the numbers, like beta equals to 1/3, delta equals to 1, now plug in those numbers first, which will make your life much more easier. Let us think that I just solved for general cases for pedagogical purposes anyway. Question F, on day 2, what kind of problem would this agent solve? So now we are going to day 2. Okay, so let me just show you what happened here. Day 1, day 2, day 3. Okay, so 3/5 of the cake is gone. The first row is for the plan. And then he was thinking that, day 2, day 3 guys will share 1/5 of the cake. Okay. Now, in reality, it will be different, right? So let's see how it can be compared. Let's see how day 2 guy will be splitting the cake with day 3 guy. So this is the big picture. Let me just delete this. So what kind of problem would this agent solve on day 2? He will solve, I want to maximize, let me go back to color blue, maximize consumption. And on day 2, day 3, then my utility function looks like log of C2 plus. Now I'm using beta delta here. I'm a present biased guy. If I come to day 2, now I discount with beta delta. So I discount all future consumption with beta, and then I'm using discount factor delta for each day. This is different from what day 1 guy thought. Day 1 guy thought that when I discount C2 versus C3, you can see that the only difference between beta delta and beta delta squared is just 1 delta. So he was thinking that day 2 guy is going to discount by delta, which is wrong. And they follow through this plan, which is wrong. In reality, day 2 guy will be solving this. Subject to the condition C2 plus C3. How much cake do we have left? It is 2/5. So let's see how this guy splits this cake. So set up a Lagrangian. Lagrangian is what I want to maximize plus beta delta log C3 plus lambda. So lambda for the budget constraint. Now budget constraint is 2 over 5 minus C2 minus C3. And then let me get the first of the conditions. F or C. We have 2 things to control. So let me differentiate this twice with C2 and C3. Differentiating with C2, set it to 0. We have 1 over C2 minus lambda. If I differentiate with respect to C3, set it to 0, I will have 1 over, beta delta 1 over C3 minus lambda. And then we have our budget constraint. So this star, 2 star, 3 star. Okay, any questions so far? Now let me rearrange the first of the conditions. How much would he actually consume on day 2 and day 3? Let's see. C2 equals to 1 over lambda. C3 equals to beta delta 1 over lambda. I was using 3-star equation for this, 2-star equation for this. And then this is beta delta C2 using this one above. Then using the budget constraint, 1 star, we have C2 plus C3, which is, now let me put it here, C2 plus C3, which is C2 plus beta delta C2. Well, this is coming from here. It adds up to 2 over 5. Okay, we are done. So C2, and if I proceed from here, C2 1 plus beta delta equals to 2 over 5. So C2 equals to beta is 1/3, delta was 1. Okay, so we have 1 plus 1 over 3, 2 over 5, which is 4 over 3, 2 over 5, 8 over 15. And then C3 is just the amount of cake that we started with, 2 over 5, minus 8 over 15, which is I was stupid here. Sorry, guys. I made a small mistake. I made a big mistake here. Sorry. So C2 is 2 over 5 divided by 1 plus beta delta. And I was multiplied by this. Oh, I'm really sorry. And then this is 2 over 5. 1 over 1 plus 1 over 3. So beta is 1/3, delta is 1. So we have this. And then we have 2 over 5, 1 over 4 over 3, which is 2 over 5 times 3 over 4, which is 10 over 3. Okay. Then what is C3? C3 is 2 over 5 minus 3 over 10. 2 over 5 minus, let me write like this first, and then C2 was 3 over 10. So we have 3 over 10. This is 1/10. Okay. Let me label this. This is the actual consumption. Actual consumption. Okay. Actual consumption is here and here. Compare that with planned consumption. What I was when I was making a plan, I thought that guy on day 2 will consume 1/5, so 20% of the cake. Let's see. He's on day 2. Actually, I'm consuming 30% of the cake. So this greedy guy on day 2 is consuming more than I originally planned. So the poor guy on day 3, he is only left with 10%, 1 over 10, 10% of the cake. I was thinking that he will have 1/5 of the cake, but no. On day 3, because day 2 guy is too greedy, he's leaving small portion of the cake for the guy living in day 3. Yeah, so this is the implications of using a naive agent. Any questions? Okay, now we use sophisticated agent, slightly difficult, but no, and maybe this can be much more easier. So we are using a sophisticated agent. So how do we solve this? When we are solving naive agent, we are solving at once. So we were, so he was thinking that my plan follows through. So I was just solving at once, get the plans, and then we were done. The sophisticated agent is not stupid like naive agent. He knows what the future agent will do. Okay, so when I want to solve for day 1, day 2, and day 3. So starting on day 1, I need to think about what day 2 guy will behave. So I first solve how day 2 guy will behave. Using that, I solve the whole problem. So it's like solving the problem backwards. I start from terminal date, the final date, and then move backward. So this is called backward induction. So think about how greedy day 2 guy will behave. Then I make my plan based on how day 2 guy will behave. Okay. So let us solve this using backward induction. Question A. What does it mean to be sophisticated? So I just explained. Would sophisticated agent follow through the plan? Yes, he is sophisticated. So when he's making a plan, it is a very deliberate plan. Okay, so he thinks what the day 2 guy will think, and then make the plan. So his plan will be the same as the actual consumption. So let's see. Describe how a sophisticated agent will solve a backward induction problem. So how do we solve this? Step 1, we think about how guy on day 2 will solve the problem. So maximize C2, C3, log of C2 plus beta delta, log of C3, subject to C2 plus C3 equals to what is left from C1. So based on what is left on C1, I want to conjecture how the guy living on day 2 will behave. Okay. They get, what do? I just get C2 as a function of C1, C3 as a function of C1. What is this? How my future selves behave based on my choice. C1, my choice of how much cake do I eat today. So I first think about how future guys will behave, and then make my choice. Then, as a step 2, we maximize using C1 beta delta log of C2 as a function of C1 plus the. Now this notation can be confusing, so let me move this to here. Delta squared log of C3 is not just C3, it's a function of C1. Okay, so we solve the problem in this way. So this is the backward induction. Any questions? Okay. So how about exponential discounter? This guy, beta is 1. So today his beta equals to 1. Tomorrow his beta is also 1. So for this guy, yes, he's kind of sophisticated. So we don't really say that this guy is sophisticated, but he's sophisticated in the sense that his plan is equal to his actual choice. So he follows through the plan because there is no time inconsistency. So let's see how exponential discounter will solve this problem. Is beta equals to 1? This is 1. This is 1. This is 1. So when he makes a plan at once, so using backward induction and solving the problem as a whole will give the same answer. So for exponential discounters, he will follow through the plan. Yeah, this is a simple answer. And then, so come back to sophisticated agent. And copy and paste this one. Let us use backward induction to solve this problem. So we are solving backward. So Lagrangian will be log C2 plus beta delta log C3 plus lambda 1 minus C1 minus C2 minus C3. You might be wondering how I am writing this budget constraint in the Lagrangian. So usually we put the controls. So what we want to control here, here. And then here we just put something like the piece of cake left at the front. Okay. So the amount of cake comes first, and then we put the arguments that we want to control or maximize. Okay. And then FOC is differentiate Lagrangian with respect to C2 becomes 0. This is C2 minus lambda equals to 0. And then, because we did similar things many times, let me move faster. If I differentiate with respect to C3, we have 0. And then this becomes beta delta. C3 minus lambda. So C2 plan is actually C2 actual. So it's the same. So let me just drop this. C2 is 1 over lambda. And then C3 is beta delta 1 over lambda, which is beta delta C2. So this implies that C2 plus C3 was supposed to be 1 minus C1. This is coming from here. And because C3 is beta delta C2, we have beta delta C2, 1 minus C1. So we have C2 equals to 1 minus C1, 1 plus beta delta C3. If you do it, so C3 is beta delta C2, which is 1 minus C1 multiply beta delta 1 plus beta delta. Yeah, I understand it. I'm going a bit fast. Yeah, so I'm sorry for that. So this part was coming from here, like this. And then step 2. Now, the final piece of this backward induction, just substitute in the answers into here. C2 goes to here. C3 as a function of C1 goes to here. Then I want to maximize I just need to control for C1 now, because C2, the value of C2 and C3 will be automatically determined by this pink box. Okay. So log of C1 plus the delta log of 1 minus C1, 1 plus beta delta squared log of 1 minus C1 beta delta 1 plus beta delta. Okay. I also forgot to put beta equals to 1/3, delta equals to 1. So we can do it later. Yeah. So FOC, the first of the conditions for this will be 0 equals 2. So we just differentiate this this expression above. 1 over C1 plus beta delta. We use chain rule here. I first differentiate this log function, which gives 1 plus beta delta over 1 minus C1. So this number is flipped. And then I differentiate with respect to C1. So this part. Then I have minus 1 plus beta delta plus beta delta squared. So now I'm dealing with this part here. So same, flip the log. 1 plus beta delta 1 minus C1 beta delta times, now I differentiate with respect to C1 for this part. Then I'll have beta delta minus 1 plus beta delta. Okay, that doesn't look very nice. So we can see that this one can be cancelled out. This one can be cancelled out. Beta delta can be cancelled out. Okay, that's it. Then we have 0 equals to 1 over C1 plus, let me take out this minus to the front. Then we have minus beta delta 1 minus C1 plus, minus again, minus beta delta squared 1 over 1 minus C1. Okay, that doesn't look very bad. And then now, let me multiply C1 and 1 minus C1 at the both hand sides of the equation. Then I will have 0 equals to 1 minus C1. Now C1 in here is gone. Now I have minus beta delta C1. This part is gone. Minus beta delta squared C1. So 1 equals, yeah, so this equals to 1 plus beta delta plus beta delta squared C1. So I'm just combining this one, this guy, this guy. Look at this. Then C1 equals to 1 over 1 plus beta delta squared. Okay. And then what is C2? Now C2 is this, okay, this guy. 1 minus 1 minus. So for this one, because the algebra is getting complicated, let me just plug in the value of beta and delta here. So beta was 1/3, delta was 1. If I solve this, it is 1 over 1 plus 1/3, 1/3, 3 over 5. C2 is 1 minus C1 times 1 over 1 plus beta delta, right? Yes. So this is 2 over 5 times 4 over 3, which is 3 over 10. C3 is 1 over 10. Yeah, yes, that's correct. Okay. Okay. So this is actual. Also, it's same as the plan, because if I'm sophisticated, plan and actual consumption will be the same. So that wasn't easy. Any questions? For the final piece, for the remaining 5 minutes, there's one good pro tip of solving these type of questions. Actually, we don't even need to set Lagrangian to solve this. Really simple way of solving this is that, suppose that I want to maximize like something like this, beta delta log of C2, beta delta log of C3, and beta delta cube log C4. So give me any number of period. If you have log utility, we did constraint C1, C2 plus C3 plus C4. It doesn't have to be 1, it can be any number W. Okay. Then, so this is what you can use in the exam if you don't have much time left. C1 will be 1 over 1 plus beta delta squared plus beta delta cube. C2 will be beta delta squared plus beta delta cube. So the trick is that add all discount factors. So this guy at the 1, beta delta squared, beta delta cube. So put that into the denominator. On the numerator, you will have the coefficient for each consumption. So even without solving this using Lagrangian, we already know what the answer is. So in the same way, C4 will be beta delta cube, this guy on the as a coefficient, over 1 plus beta delta squared plus beta delta cube. So this is using the property of Cobb-Douglas function, so which I was trying to explain in the bonus question. I will write the answer key for this one and then share this on Canvas. Okay, so it was not the most exciting discussion, however, but thank you guys for bearing with me, and see you guys next week. Thank you.